Hello everyone. So we are going to discuss electric field in this video. So let's recall what we discussed last time. So if you have two positive charges, they're going to have a repulsive force on each other. And the concept of electric field was introduced based on the concept of electric force. Now, if you put positive charge A here and a positive charge B here, we think we're going to have a force, let's call it F0 on the charge Q0. Now think if you remove the charge Q0, you only put QA here. Now what we think of is that this charge A has modified the property at this location point P. And we say this is the electric field produced by charge QA at location P, such that if we put a test charge Q0 here, its force is going to be F0. So electric field was defined as the force on a test charge divided by the magnitude of the charge carried by this test charge. And this is a vector equation, which means electric field is in the same direction of F0 receiving by this testing charge. They're in the same direction. Now if you have a charge QA positive, then the electric field is always pointing away from this charge. And if you have a positive charge here, you're going to have a force in the same direction as E. This Q0 is positive. On the other hand, if you put a Q0 negative here, apparently we learned that they should attract, so the force on the negative charge should be pointing into the positive charge, but the electric field is still pointing away. Now remember the equation we have is F0 equals Q E0. So if your Q is positive, F in the same direction of, this is Q positive, then F in the same direction of E. If your Q is negative, then your F is Q0E, right? And the negative means your F is going to be in the opposite direction of E if your Q0 is negative. So we're ready to define what will be the electric field generated by a point charge. So we're going to use a unit vector r, which is in the direction from the positive charge to where you want to find out what's the electric field. So that's the direction. Its magnitude is 1. So E would have the same direction of R. Then we know what is magnitude of this E using Coulomb's law, right? From Coulomb's law, the force between Q and Q0, F0 should be K Q0 over R squared. This is magnitude, and the E is F0 over Q0. So basically, you eliminated this Q0. This is the magnitude of this force. And now if you want to put the direction there, E is in the same direction as R hat. And R hat has magnitude 1. So you keep what's your magnitude for your E in the same direction of our head. So this is going to be the electric field generated by one point charge. And this is what we have. The only difference is that we also need to understand that K equals 1 over 4 pi epsilon 0. K is Coulomb's constant. Epsilon 0, we call it the vacuum permittivity. Now, go back to the electric field generated by point positive charge again. Now, a point charge produces an electric field at all locations in space. Because of E is proportional to 1 over r squared, of course, if you are far away from the charge, the electric field is going to be smaller or weaker. If you get close to the charge, it's become stronger, as we can see from this 1 over r squared. And for positive charge, all the electric field at all locations is pointing away from the charge. On the other hand, if you have a negative charge, the negative charge creates an electric field at all points in space as well. And we also have this 1 over r squared relation. So strength decrease with distance from the charge. But this time, remember, the electric field produced by a negative charge is pointing into the charge. So for positive charge, electric field pointing away from the charge. Negative charge, electric field pointing into the charge. Now if you have more than one charge, you need to add the electric field produced by each charge together as vectors. Why? Because electric field was calculated based on electric force, right? And we learned from last class that if you want to add electric force from different charges together, you need to add them as vectors. So this is why if you want to add the electric field produced by different point charges, you need to add them as vectors. So let's do one example to help us understand this vector relation. So now we have 3 negative charges. They are arranged in such a way. Each time, so let's call this one Q1, Q2, Q3. Q1 and Q3 have the same magnitude, negative 5 microcoulomb. Q2, negative 2 microcoulomb. Q1, Q2, 8 centimeter, Q2, Q3, 8 centimeters. They are all in y direction. Let's call this to be y direction. And then this is our x direction. We want to find out what is the electric field produced at this point P, which is 6 centimeters away from Q2. So let's do some trigonometry first. So of course we need to find out the distance from Q1 to P. We need to find out the distance from Q3 to P. Now this is a right triangle. This is 6 centimeters. This is 8 centimeters. So if you use Pythagorean theorem, 8 squared plus 6 squared centimeters will give you 10 centimeters for the distance from Q1 to P. Also do the same. This is 10 centimeters from Q3 to P. Now we also need this angle, the angle between Q1P and Q2P. So we can use trigonometry to find out this angle is 53.1 degree. So we said we need to add those vectors, those electric field as vectors. So you need to find out the electric field produced by Q1 at P, by Q2 at P, Q3 at P vectors. Anyway, we need to find the magnitude, right? So let's first find the magnitude. Basically, this is going to be E1, this is going to be E2, E3, this is going to be E2. Let's find the magnitude of E1, E2, E3 first using Coulomb's law. So E2, let's find the E2, which is easier, right? E2, K, Q2, R2 square. R2 is 6 centimeter, which is 0.06 meter. And K is 9 times 10 to the 9. Q2 is -2. So if we want to find out the magnitude, negative doesn't matter too much. So 2, 10 to the, because it's microcoulomb, right? -6. This is Q2 over R2 square. R2 is 0.06 square Newton per coulomb. Number is 4.99. 10 to the 6 Newton per coulomb. This is magnitude of E2. Now we need to find out the magnitude of E1 and E3. E1 and E3 has same amount of charge. E1 and E3 has same amount of charge. They are both -5 microcoulomb. So, and the distance from Q1 to P equals distance from Q3 to P. So you can imagine E1 and E3 have the same magnitude. So let's use E1 for the calculation. We put a Q1 here, R1 here, plugging all the numbers. The distance is 10 centimeter, which is 0.1 meter. So now at least we find out what's the magnitude of E1, what's the magnitude of E3, what's the magnitude of E2. Now we need to add E1, E2, E3 together as vectors. So let's do the y direction first. What is E1, E2, E3 add up in the y direction? You need to find out E1y. And you need to find out E2y, you need to find out E3y. Now, E2y apparently is 0 because E2 is pointing in the entirely negative x direction. E2y is 0 and E1y, if you know, remember the vectors, E1y should be E1 times cosine theta, let's call it theta 1, would be the angle of E1. So I would think theta 1 equals 90 degree plus this angle, which is, let's see, 37.9 degrees. So this is theta 1. And then theta 3 is from 0 degree to E3. Theta 3 actually, I think is 180 degree plus 53.1 degree. And okay, E3y is for the y direction it will be sine theta 1. E3y is E3 sine theta 3. So if you plug in those two numbers, you will find out E1y equals negative E3y. So E1y plus E3y is 0, which gives us EY is 0. Okay, so in the y direction. is 0 if you add E1, E2, E3 together. Now in the x direction, so Ex would be E1x plus E2x plus E3x. E2x is just whatever E2 is. E2x is negative 4.99 10 to the 6 Newton per Coulomb. E1x, this time you need to use cosine E1, cosine theta 1, E3x, E3, cosine theta 3. Plug in those numbers. Its magnitude actually is 2.69 10 to the 6 Newton per Coulomb. And this one you will find it equals E1x equals this number. You put everything together, you find Ex. Of course, E1x is negative. So put everything together, you find Ex is negative 1.04 times 10 to the 7 Newton per Coulomb. So this is a demonstration how we need to add electric field produced by different charges as vectors. Another concept is electric field length. So electric field length is not realistic, it's an imaginary number. That if you have electric field line, if you choose the point on the line, then you do the tangent line to give you the direction of the electric field at this point. Pick any point on the electric field line, do a tangent, it will give you a direction of the electric field. So electric field line is not real, but it's very instructive how electric field looks like and how we do more complicated calculations. And we use the density of the electric field to represent the magnitude of the electric field at that location. So this is how electric field looks like for the positive charge, and this is the electric field looks like for pair of positive and negative charge. So the electric field pointing from positive charge and pointing away from positive charge towards the negative charge. You have strong electric field here, very weak electric field here. Okay. So now for another example, let's study how charged particle move inside an electric field. So we have two plates. Now let's just see, we know these two plates create electric field, homogeneous electric field, pointing from top plate to bottom plate. So you can imagine this one will carry positive charge, electric field pointing from positive charge to negative charge. And they are homogeneous. So electric field is the same everywhere. You shoot an electron into this electric field with the initial velocity 1.6 10 to the 6 meter per second. So let's see, it says an electron doing a motion like this, and the electron enters the field midway. Electron just miss the upper place, so go out from here. So using this information, it asks us how to find out the magnitude of the electric field. So how are we going to think of this program? So we know if you want to find the electric field, this is kind of kinematic problem. Kinematic problem can give us A, acceleration. And then from acceleration, you can have force. Force is ma. Now, in the vertical direction, the only force acting on the electron is electric force, if we can ignore gravity, right? So we'll see whether we can ignore gravity in question D. So now let's just pretend we can ignore gravity. F equals ma, and we know it should be E times the charge of E times E. So if you can find out A, and the mass of electron is a constant. So basically, if you can find out what is A, you can solve for your E. So I need to solve for my A. So in the x direction, let's first say in the x direction, what kind of information we can have? Is there any force in the x direction? I would think no, right? There's no force in the x direction. So with the initial velocity, the electron is going to do a constant velocity motion because there is no force, no acceleration in the x direction. So x direction, constant velocity motion. And we said if you have constant velocity motion, the only equation you need to use is displacement equals v times t. And it seems we know what is delta x, right? 2 centimeter. We know the velocity. Which means we can find out t, which is 8, right? Let me see. Not 8, t, 1.25, 10 to the negative 8 second. So this is the time it takes for the electrons to go from here to here. Already found as a time. Good. From the information in the x direction. Now we go to y direction. We see in the y direction there indeed is a force, which is the electric force acting on the electron. And the electron will have a constant, will have an acceleration due to this force, right? And the acceleration is going to be a constant. So the electron is going to do constant acceleration motion in y direction. So look, what kind of information do we have? We want to find out what is acceleration. We know what's the displacement in y direction. From here to here is 0.5 centimeters. So delta y is 0.005 meter. I know what is displacement in y. I know what's initial velocity in y as well, right? So initial velocity is entirely in the x direction. So initial velocity in y direction is 0. Good. I found 2 informations. I just need one more information in y direction so I can solve everything for constant acceleration motion. If you remember how to do constant acceleration motion program. So we have 5 equations, right? We have 5 variables, and each equation has 4 variables. So if you know 3 variables, you can always find the 4th one by picking the correct kinematic equations. So I know two variables. I need to find the 3rd one, which of course I need to get it from x direction for this kind of a motion, which is t. So you need to find the equation for those 5 equations in constant acceleration motion, that which one has acceleration, displacement, initial velocity, and t. If I remember correctly, it should be the third one, that y equals v0 y t 1/2 a t squared. Now your v0 y is 0, you know your delta y, you know your t, you can find what's your a. So your ay is 2 delta y t squared. You plug in all the numbers, you find is a huge acceleration, 6.4 to the 13 meters second squared. So now I'm ready to calculate what's my E, right? From here. So E is going to be mass of electron AY, which I just solved, divide by charge of electron, which is 1.6 10 to the negative 19. Plug in all the numbers, you find your E is 364 Newton per Coulomb. Okay, now bullet B asks us if you change electron to proton, what's going to happen? So if you change it to a proton, your electric field pointing this way, what's going to be the electric force on the proton? Pointing down, right? And it's going to be Q proton times E. So the force is not going to change. So it's going down, force is not going to change. And the motion in the x direction is not going to change either, right? There's no change, anything changing in x direction. Initial velocity, no force, no acceleration, constant acceleration. But in the y direction, the force doesn't change. However, you change an electron to a proton. So you need to Google what is the mass of a proton and then what is the mass of electron. And you will find out the mass of proton is much larger than mass of electrons. So the acceleration is going to be different because mass is not the same anymore. The acceleration for the proton is going to be 3.49 10 to the 10th meter per second square. T is still going to be 1.25 10 to the negative 8 second we discussed. The same in the x direction. So the deflection for this proton, its acceleration is small. Let's calculate first. v0yt plus 1/2 apt squared is going to be a very, very small deflection for proton. And so we basically already argued why it's different. So because you have different sign of charge for proton and electron, so electron is going to move upward, so electron is going to move upward, and the proton is going to move downward. You have the same electric force on electron and the proton, but because the mass of electron and the proton are very different, AP is going to be very smaller compared to AE, so the deflection of proton is not going to be so large compared to the deflection of the electron. And can we ignore gravity in this example? So you can check what is AP is in the 10 to the 10th power. What is acceleration of electron? 10 to the 13th. What is acceleration due to gravity? Ag 9.8 meter per second square, much smaller than 10 to the 10th meter per second square, and even smaller than 10 to the 13th meter per square. So the effect of gravity is very, very small, negligible compared to electric force. This is why we can ignore gravity in this calculation.